Justin Miller, Oxnard College Physics here. Did you hear that? You know why? Because of sound waves. That's right. So I make a little clap, produces a disturbance, and you hear it. Well, you hear it because the sound travels from my hands to the microphone of my camera and then comes out your speakers. But if you're in the room with me, you would hear it with your ear because of the disturbance traveling through air to your ear. So how does it travel? This is what we want to start looking at, is sound waves. So ultimately, sound is due to some disturbance. There is some source of vibration. And that vibration, what it does when we're in air is it vibrates the molecules right next to the source. So my hand undergoes a little vibration, the air molecules right next to my hand undergo a little vibration too, just like my hand vibrates. And those little air molecules that vibrate back and forth right here, vibrate the ones that are next to them. And those vibrate the ones that are next to them, and next to them, and next to them, and next to them, and next to them, until whoop, the ones right next to your eardrum vibrate, and actually interact with your eardrum and activate little sensitive nerve cells that perceive particular frequencies of vibrations, and it's translated into sound. So ultimately, what do we need for sound? We need some sort of media for the wave to travel through. And typically we're dealing with air. Sound can travel through other gases and other solids and liquids, but we're going to mostly deal with air here, so sound traveling through air. We've got air molecules all over the place, and those air molecules are responsible for allowing the vibrations of some source to transit from the location of the source to wherever it's being perceived. But it's not that the air molecules are moving from the source to wherever they're perceived. It's a cascade vibration kind of domino effect that occurs. The air molecules just vibrate really slightly back and forth about some standardized equilibrium position. So what we want to do is have some model for this behavior and then discuss aspects of sound so we can coherently talk about it. And that's basically that. So we're looking at sound waves. Exclamation point to make it nice and loud. All right, so we can talk about sound waves in two different aspects. And right now we're going to be dealing with singular frequency sound waves, and that's another matter here. But ultimately we can talk about pressure variations that are occurring throughout space and time. Those pressure variations are really correlated with how the molecules of air bunch up or spread apart as they vibrate back and forth and transit the sound as a wave. So there's really two aspects of it. We can talk about the displacements of the individual air molecules as they vibrate back and forth, or we can talk about the changes in pressure at particular locations that inevitably is due to the oscillation of those little air molecules themselves. Where air molecules bunch together, we have high pressure. Where they're spread apart, we have low pressure. And ultimately, again, that's going to be due to all of the air molecules vibrating back and forth as the sound is sustained. So we can talk about displacement. We have delta S, I'm just going to call it S of x and t. Displacement as a function of position and time is equal to S max times the cosine of kx minus omega t. Don't care about a phase constant in this case. We just care about the angular frequency, the wave number, and the maximum displacement. So S max is the max displacement of molecules as they oscillate back and forth. K equals the wave number. Omega is the angular frequency. We got x is the position and t is the time. So this is what we've got, the actual displacement of air molecules. Or we can talk about pressure. We have some change in pressure, delta P of x and t is equal to some delta P max times the sine of kx minus omega t. Delta P max is the max change in pressure, and that is relative to ambient normal pressure when the sound isn't there. If you want atmospheric pressure, if you're at 1 atmosphere, we got that. And then K and omega, same sort of correlations with that. So pressure variations with respect to time, or displacements of the air molecules with respect to time, and that's what we've got. Notice something about this, that one goes as cosine, one goes as sine. Ultimately, they are out of phase with one another by, that's it, by the difference between sine and cosine, 90 degrees, or pi over 2 radians, or a quarter of a cycle. Why is that? Well, when there is no displacement of the air molecules at a particular location, what do we end up having? 0 displacement. But it's at that position, at that particular position, where all the ones around it have either bunched towards it or spread backwards towards it. And that gives us a high pressure zone, in a sense. So when we have no displacement of the air molecules, that's where we have the maximum pressure. And when we have the maximum displacement of the air molecules, that's when, again, at one location where everything's spread apart from its equilibrium position, maximum distance away, and what do we get? We get a low pressure there. So ultimately we can think of sound traveling in pressure variations that are due to correlations of, again, the vibration of the air molecules. We can talk about it in terms of compression zones and rarefication zones. Compression zones where we have a large number of particles per unit volume, in which we have high pressure, or a rarefication zone where we have a small number of molecules per unit volume, and that correlates with low pressure. So that's how these two kind of fit in with one another. We're not going to be so interested with this other than it's sinusoidal, great, and again, we're talking about singular frequencies. So here we are sticking with singular frequency sounds. Also note, sound travels as a longitudinal wave. The sound travels in the direction that it's traveling, and the air molecules vibrate back and forth in line with the direction that it's traveling. So, sound travels as a longitudinal wave, unlike the transverse waves on streams. All right, so like I said, we're not so much interested in the wave feature there. We're more interested in things like, what about the speed of sound? And what about the intensity, the loudness? How do we start quantifying things like that? So those are the things that we're going to stick with regarding sound and make some nice generalizations here. So first off, the speed of sound. Is, well, it's the same thing that we had with the speed of any wave. It's going to be omega over k. Depends on the angular frequency and the wave number, which correlate again with the period and the wavelength. For air, well, speed of sound is temperature dependent. As we find in many cases, speed of sound has some correlation with what temperature that substance through which the sound is traveling is at. But generally speaking, we're going to be dealing with sound traveling through air, so we need some sort of notion of what the actual speed of sound is and how it varies with respect to temperature. This is just by definition in terms of the frequency and the wave number, but these two, the ratio of these two numbers has to work out to be the speed of sound. So the speed of sound in a given substance really depends on some bulk properties of the substance and the elasticity of the substance. Much like we had with waves on a string depended on the tension in the string and the linear mass density. We have the same sort of correlations with the speed of sound through a substance. We're not going to really get into that much, but note that for the speed of sound in air, we have that V sub air is equal to 331 meters per second multiplied by the square root of 1 plus T sub C divided by 273. There's a nice first order approximation for the speed of sound in air, given that we have the temperature in Celsius. Temp in degrees Celsius. So what do we have? Well, at 0 degrees Celsius, the speed of sound in air is 331 meters per second. Great. Well, at T sub C is equal to 20 degrees Celsius, which is room temperature, considered to be room temperature, around 72 degrees. V sub air is equal to 343 meters per second. And this is approximately, there's some little more significant figures there, but this is what we generally use for the speed of sound in air at room temperature. 343 meters per second. Sounds pretty fast. Sound is pretty fast. It sounds pretty fast and sound is pretty fast. Anyways, that's what we've got. And as we keep increasing the temperature, we keep getting higher and higher on the speed. Anyways, this is something that will pop up in some problems here and there, varying the temperature and all sorts of good things. But if the temperature isn't stated, or it just says 20 degrees Celsius, you'll use 343 meters per second, which is about 1,128 feet per second, which is approximately a fifth of a mile per second, right around there. That's not exact by any means. So for sound to travel a distance of a mile, it takes approximately 5 seconds. So I remember when I was a kid being told, like, lightning striking, you see the lightning flash, and you can start counting right when you see it, and the number of seconds that goes by until you hear the thunder associated with the lightning means that that strike was 1 mile away from you for every second that went by. And that's grossly wrong. The idea is good, but that's really, really wrong. Every 1 second is 1/5 of a mile. So I remember counting and thinking, oh, it's pretty far away, when it was 5 times closer than I thought. Whew. Anyways, maybe you've seen like fireworks and stuff, right? You see the flash and then, ooh, maybe a second later, a couple seconds later, you hear the boom, pop. Because the speed of light is extremely fast, just about instantaneous over small distances, where the speed of sound, hey, it takes a little bit of time to get to you. And that's why we have this offset often for big sounds that are far distances away from us. Anyways, that's what we've got. So, what else can we do with this stuff? Well, one thing is we can make a correlation between the maximum change in pressure with respect to the maximum displacement of air molecules. So I'm not going to derive this, but it's just a nice expression to correlate the two because they are connected with one another. And that is that delta P max, the maximum change in pressure, is rho V omega S max. All right, so we've got these things going on for us. What are these? Well, rho, again, rho is the density of air. And for the density of air, if we're at sea level and it's 20 degrees Celsius, we've got approximately 1.20 kilograms per cubic meter. And that is approximately, but that's something that we'll use in some problems from time to time. As you go up higher and higher, the density of air gets less and less. And as the temperature increases, it gets less. There's all sorts of things that happen with density. But there's the density of air. V is the speed of sound. Omega, we know what omega is, and S max, we know what S max is. We got the angular frequency and the maximum displacement of the air molecules themselves. So this again just gives us a correlation between those two quantities that are in those two wave functions, in a sense. All right, so that's a nice. What else can we do with this? Well, what we could do is now start talking about power. And we actually looked at it already for waves on a string, and we could go through and derive it again. Velocity, force, such things, pressure and displacement. Pressure is correlated with a force per unit area, and we got displacement, there's work done. Work done equates into what? Energy, right? So we can look at energy per unit time, average energy per unit time transmitted, or that is there to produce the sound. And we get something very familiar. And again, for this, I'm going to spare the derivation because it's very similar to what we had done before with power transmitted by waves on a string. A little bit different because we got some different quantities, but we have this. Power transmitted by sound. So the average power transmitted by sound, and this would be the average over one cycle time-wise, is equal to 1/2 rho A omega squared, 1/2 rho A omega squared times a V times S max squared. 1/2 rho A V omega squared S max squared. Yeah, this is it. So what do we have here? Well, again, we've got the maximum displacement of the air molecules. We've got the angular frequency correlated with the sound. We've got the speed of sound. We've got the density of air. And again, this is transmitted by sound through air. And then we have this A here. Well, this A is not the amplitude, because the amplitude is correlated with S max, right? The amplitude of the oscillations of the individual air molecules. What is this A? A is the area being considered. What area? Maybe it's the area of your eardrum, and you want to talk about the energy per unit time arriving at your eardrum, which would be the power. Or you're talking about the source producing it, some speaker vibrating back and forth. The speaker has some area that undergoes the vibrations that's producing the sound, and that would be the area under consideration. So it is dependent on the area, not the amplitude of the oscillations. That's right there. So what can we do with this? Well, we can define another quantity. Well, this is important and nice. What we really want to get to is what is known as intensity. We now define intensity of a sound. Intensity I is power per unit area. SI units of intensity, well, what's power? Watts, that's right. What's area? Meters squared. So we've got ourselves watts per meter squared is intensity. So we just talk about watts per meter squared. Don't name that something else. So that's 20 watts per meter squared, bam. Anyways, that is power. Now, if we're talking about, intensity. If we're talking about the intensity of a sound wave, I is then going to be equal to the average power divided by area. And we can say that this is the average intensity. It is time varying, but it varies very quickly, and really we want it over one cycle. So we've got this, which then gives us 1/2 rho omega squared S max squared times V. Change the order a little bit, but ultimately we just get rid of this A right there. There we go. There is the intensity of a sound wave. And intensity correlates with loudness. The more intense the sound is, the louder it is. But intensity depends on where you are relative to the sound and the cross-sectional area over which, the power depends on the cross-sectional area. And the maximum displacement of the air molecules that are occurring. So generally you have the source. The source produces these relatively large displacements of air molecules right next to it. But as you move further and further away, what ends up happening? Well, you get a decrease in the intensity. Why is that? Why would you get a decrease in the intensity? And really what it comes down to is it comes down to the area over which the sound waves are constrained to. That ends up getting spread thinner and thinner and thinner, or being a larger area over which the same power is constrained to. So, I'm going to be a little confused right now. To clear this up. We consider a source of spherical wavefronts. We have that the sound travels radially outward. Radially outward in all directions at the speed of sound. So consider this. We've got this little source here. Here's our source undergoing some vibrations, little spherical source. And around this source, we could sort of draw out wavefronts. Let me draw a circle first, then put the source there. That's already bad. So we've got this distance, this distance, this distance. Try this. Harder than it seems for me to draw a circle. Okay, so what's the deal with this? Well, the deal with this is this would be considered to be one full wavelength, as would this would be a full wavelength, as would this be a full wavelength, as would this be a full wavelength. So the spacing in between these dotted lines represents like the peak of the wave, the maximum amplitude of pressure, or really anything, any starting spot. But this is what we've got. These are all wavelengths. So we've got in any one wavelength that this would be the wavefront that's traveling outward. So everything's moving outward in all directions. Speed of sound. That's not what I had. So that's why we get that it gets bigger and bigger and bigger in any one wavefront as time goes on. Well, the energy that's constrained to a wavefront is a constant value. It was produced by the source, and then what happens to that energy? Well, that energy remains there, it just gets spread thinner and thinner and thinner. The area over which that energy is spread out, think of these spheres, well, the spheres get larger and larger. So what happens to the energy? The energy gets spread thinner and thinner. Thus what happens? Well, although the power remains the same, energy per unit time remains the same on any one wavefront, the intensity decreases because the area has increased. So, we'll say the energy associated with a wavefront is constant. As it spreads outward, well, it's the same. The amount of energy on this wavefront is the amount of energy on this wavefront, is the amount of energy on this wavefront, and so on and so on and so on. But the area it is confined to is larger as it spreads outward. Thus, there is a decrease in intensity. All right, so what do we do with this? Well, we can go ahead and make a direct correlation with the intensity, the power, which again is associated directly with the energy, which remains constant on any wavefront, and the area to which the energy is constrained. So we can write for spherical waves spherical wave fronts, intensity is equal to average power divided by the area of a sphere. What's the area of a sphere? 4 pi r squared. That's right. 4 pi r squared. Where what's r in this case? R is your radial distance away from the source. Your distance this r away? Well, there's a certain amount of energy per unit area here, power per unit area, and that correlates with the intensity. You're further away, hey, there's less energy there because it's been spread thinner at a given area, like your eardrum. So let's just say where r is the radial distance from the source. So this is important because it correlates nicely with the variation in intensity with respect to position. The further you are away from the source, hey, the softer it sounds, or the less loud it sounds, because its intensity drops off as 1 over r squared. Double your distance away, the intensity drops off to 1/4 of what it was. And there we go, sort of things like that. All right, so at this point, what we want to do is really talk about intensity. That's what all this was to get to, the idea of intensity. What's intensity dependent on? Well, it depends on S max, maximum displacement of the air molecules. The greater the displacements, maximum displacements, the louder something is. That's a direct correlation right there. Yeah, it depends on the frequency too, the wave speed, the density of air and such things. but it's heavily, heavily dependent on both the frequency and the maximum displacement of the air molecules. The frequency is something that's controlled by the source itself. That is to say that, hey, you produce a sound at 392 hertz, 1,000 hertz, 10,000 hertz. That's all frequency in hertz. This is angular frequency, but they vary the same sort of way. At any rate, that depends on the oscillation of the source itself. And then how vigorously that source oscillates really largely dictates what the overall maximum displacement is, or does dictate what it is, and then that correlates with the intensity that varies with position. Whoa! All right, so what do we do with this? Well, first off, I want to talk a little bit about intensity and our human ear, and then develop some more ideas about loudness. Intensity of sound and a human ear. All right, so the human ear is pretty darn sensitive. You say, no, dogs' ears are way more sensitive. And I say, yeah, that may be true, but the human ear is pretty amazing too. For one thing, we can have all these different frequencies going on, and your ear sorts them all out, and we perceive them as, well, in often cases, people talking, right? I'm talking a bunch of different frequencies, lots of different variances, but you hear it all, and your brain can interpret it into the words that you know. Then you understand, that's not so much your ear, but your brain. But anyways, when we start talking about intensity of sound regarding the human ear is pretty sensitive. It can hear sounds between approximately 1 times 10 to the negative 12 watts per meter squared and 1 watt per meter squared. Whew, that's a pretty big variation there, right? Billion times. So you say the threshold of hearing. Generally called I sub naught, or I zero, is equal to 1 times 10 to the negative 12 watts per meter squared. Let's not do some bad spelling here. This is on average, smallest sound heard, like I change perceivable to heard. Anyways, smallest sound heard on average for the normal human being is approximately 1 times 10 to the negative 12 watts per meter squared would be its intensity. And what's that intensity falling over? That's falling over your eardrum, which has a certain cross-sectional area, so we could go back and say, well, what's the amount of power? And that'd be fine too. But this is the intensity. And then we have what's known as the threshold of pain. Ooh, that sounds like it might hurt. Threshold of pain. Ouch. And that we don't subscript with anything on this. We could put I sub pain, I pain, is equal to 1 watt per meter squared. What does that mean? Is that the loudest sound that you can hear? No, that's just where it starts to hurt you, and beyond that can cause permanent damage to your eardrum, like rupture your eardrum. That's no good. I've been to some loud concerts way up front, and man, your eardrum vibrates so much that it starts to hurt your head. But hey, that's it. That's the price we pay sometimes. Nonetheless, these are sort of the thresholds in between here of what we're comfortable with hearing. Beyond this, yeah, you can hear sounds louder than that. Eventually your eardrums rupture and then you don't really hear much at all. Ooh, that's no good. anyways, this is what we've got. Well, that's a pretty big difference, right? This is 1 billion times this. That's a large variation. If we wanted to start to plot out intensities in watts per meter squared regarding what the human can hear, we'd have to have something that went from 1 times 10 to the negative 12 to 1 and be able to tell differences. A factor of 1 billion scale. That's not too convenient, really, to be quite honest, to start to graph stuff like that out and be able to see anything. So what do? Well, it's not so much what we do, but what was done by a man named Alexander Graham Bell, who was Mr. Telephone and all of that stuff, who did a lot of studies with sounds, intensities, because those were important for transmissions of sounds, people be able to hear each other. And he came up with a nice convenient way of discussing intensities or correlation with intensities. So we define, let's not say we define, let's say let us define decibel scale. And this is deci, meaning 1/10, bell. Bell was the unit for Alexander Graham Bell, but it became more convenient to look at it at tenths of a bell. So decibels. And we note that that is dB, decibels, decibels. So we've got this. Decibel level is equal to 10 times the log base 10 of the ratio of I to I0. It depends on a reference intensity. So this would be the decibel level of a sound with intensity I. And actually, let's just call it I1. Again, we need a reference intensity, and that reference intensity is the threshold of hearing, the smallest sound perceivable. So it's comparative here. It's comparative, but this is how the decibel level scale is developed by comparison to the smallest sound that we can hear. So what can we do with this? Well, we can start to correlate intensities directly with, you guessed it, decibel levels. So if we solve this out, this is log base 10, we can take the decibel level divided by 10, take 10 and raise it to that power both sides, and then multiply it by I0. So we can rewrite this. Again, the inverse function of log base 10 is 10 to the x. So divide both sides by the 10, and we've got ourselves that I1 is equal to 10 to the, this is equal to I0 times 10 to the dB level divided by 10. That 10 comes over here, 10 to the x, there's the x, multiply by I0, and there's the correlation with intensity. So we can go back and forth between the intensity of the sound and the decibel level of the sound. So what can we do with this? Well, what happens if I1 is equal to I0? If we're talking about the decibel level of the smallest sound perceivable, well, this becomes the log of I0 over I0, which is the log of 1. What's the log of 1? Say, log of 1 is equal to 0, which means the decibel level is equal to 0. So that's where we start the scale at. the sound that's at the threshold of hearing. But then we start going up from there. We say, well, what if I1 is equal to 1 times 10 to the -8 watts per meter squared? Well, then we've got 1 times 10 to the -8 divided by 1 times 10 to the -12, which is what? 1 times 10 to the 4th. That's right. So we take this 1 times 10 to the 4th, take the log base 10 of it, and multiply it by 10, and what do we get? 40 decibels. The intensity of 1 times 10 to the -8 watts per meter squared correlates with the decibel level of 40 dB. And we can keep going up here. We can say, oh, what if I1 is something else? What if I1 is equal to 1 times 10 to the 4th watts per meter squared? What does that correlate decibel level wise? Well, that's going to be 80 decibels. And we'll do one more. What if I1 is equal to 1 watt per meter squared? That correlates with 120 decibels. Again, measured relative to I0 correlating with 0 dB. But this is like the decibel scale now. The loudest sound that you can withstand without falling into pain and covering your ears is about 120 decibels. Beyond that, you start to risk permanent damage to your ears. So, I should note this, that although this is the standard decibel level scale, really it's a decibel level difference. That decibel level difference is correlated with this I0 and 0 dB. Really, we can look at the decibel level difference between any two sounds, and that correlates with the ratio of the intensities between the two sounds themselves. Let's write that down. We can always compare the intensity of two sounds as such. Decibel level difference between the two sounds is going to be equal to 10 times the log base 10 of the ratio of the intensities of the two sounds. So that comes into play with which one are you comparing to what? And we could say, hey, I1 over I2. I1 is the intensity sound number 1. I2 is the intensity of sound number 2 in watts per meter squared. What does that ratio correlate with? Well, 10 times the log of it correlates with the decibel level difference between those two sounds. And well, this right here tells us explicitly, this ratio tells us explicitly how many times more or less one sound is intensity-wise relative to the other. This is just the ratios of intensity. So if I1 is twice the intensity of I2, well, I1 divided by I2 is 2, which says, hey, it's 2 times as loud. And then if we look at what the decibel level difference between two sounds where we have one twice as loud as the other, would be 10 times the log of 2, which would tell us explicitly what the decibel level difference between those two sounds is. Or we can start measuring decibel level differences and figure out what the intensity ratio is. How many times more or less intent is one sound relative to the other. And that's important to be able to do. So this is really what we wanted to get at here, is this deal with intensity and decibel levels. And kind of stick with that. What we'll do is do a problem or so of this stuff and move forward. All right. All right. Till next.